Hello again, this is Raphael bringing you the fourth video tutorial on HAL, the Hybrid Agent-Based Library. And this time we're going to be doing off-lattice modeling. So we're going to first turn this square agent into a point agent. And the distinction here is just that the square agents, or the agents with the SQ, and basically anytime you see an SQ, it's referring to integer or discrete coordinates. So every agent is bound to a particular, whole number XY position, XYZ position. And anytime you see the PT, that's referring to a point in space. So it's more like if you imagine like a continuous space, we can draw a point anywhere, and the agents are being represented as points rather than as being bound to squares. So I'm just going to make that swap here. We're also going to stay in 2 dimensions. And going to import that class, Alt-Enter. We can now get rid of the import of the unstackable agent because we don't need that anymore. And so, in theory, this will work as is written. But now, say we want to take advantage of the fact that these agents are now represented as points and can be stacked onto the same grid position, and just generally make this sort of off-lattice in behavior. So one of the first things that we should probably do is change the way the cell step function works. So before we had cells dividing to neighboring positions because we only allowed one agent per lattice position. What we can do instead is, now that these agents are represented as points and don't take up any space, we can have agents divide directly on top of each other and then have them spread around with sort of Brownian diffusion. So we'll code that up real quick. So in this case now we don't need to use the division neighborhood anymore. And before I make any modifications here, I think a nice way to sort of break up your code is if you're going to change a model, you can create a new package. Just do that from the top here. And then just copy and paste so that we keep the old version as well. So anyway, right, I was going to change up this division function. So we can get rid of this code, and we can get rid of this division neighborhood. And now we'll just have the grid create a new point agent at the XY point that our cell that's dividing is currently on. So it'll be at the exact same position. And we have to obviously, or we should initialize it as well. And then we can also have some movement. So rather than have the cells sort of stack on top of each other, because if we just run it now, then the cells will basically infinitely stack. Oh, wrong thing. So we have to make sure we run the actual file that is currently selected. So you can see now they're just stacking on top of each other. So to alter that behavior, we can have the cells also sort of randomly wander. So now I'll show you guys a bit of what cell movement looks like. So we're going to get a random point in a circle. So this is going to allow for our sort of Brownian motion. We will say that the cells can move at most, say, 0.5 sort of squares away from their current position every time step. And we also need a movement coordinates that will store the XY position that this random circle point function brings up. So we'll just create that in the main grid and then use it with each cell. So then when we call this function, it will store the movement coordinates that are going to be bound between -0.5 and +0.5, or sort of a circular radius 0.5. and then we can have the cell move based on those coordinates. There's sort of two functions. There's a move square and move point, which can be used when you know with certainty the position that the cell is going to move to is a valid position on the grid. But if you don't necessarily know that, as is the case here, you can use the move safe point function, and that will basically cancel the movement if the cell would move off of the grid. So you're ensured that the cell will always remain on the grid. So we'll give it the x-coordinate that the cell currently occupies plus the movement coordinate sub 0, so that's the first of the two, and the y position, the y point that the cell occupies, plus the sort of second coordinate. So this will displace the cell when it divides. So let's see how this looks. Or sorry, when it, just in general, whenever. So you can see the cells are kind of spreading out in a circle, and also you can tell that it's slowing down significantly. So that's because we're basically just, spreading the cells out here, and there's no spatial constraint. There's nothing preventing the cells from dividing all the time. So we can impose a sort of spatial constraint based on the count at each position. So we'll do that here. So if the count at the cell's square position is less than 5, and the cell can divide, then and the cell is chosen to divide by random number generation, then we'll have it divide. Otherwise, it won't. So now we're restricting it to being 5 cells on its square at one time. I mean, it doesn't look too different, but you can see the performance is much better because we're restricting the number of cells. So these cells are moving continuously. On this visualization, you can sort of see what's going on. But what would be nicer is if we actually had a visualization that was also off of a lattice. So HAL has that built into it, and we can use that instead. So let's set that up. This is called an OpenGL window. And there's 2D and 3D versions of this, depending on if your lattice is 2D or 3D. So we're going to go with the 2D one. And we have to set some new parameters here. And obviously we have to change the type here as well. And then you can use Command P to see the list of parameters. So this one's asking for a title. So we'll give it say it's 2-dimensional. And it wants to know the number of pixels. So this is the width and height of the window. So we're going to make it 500 by 500 pixels. And then the x and y dimensions of the grid that it's going to be drawing. So that's the x and y parameters up above defined here. So now we also have to change the draw function to use this new type. So change this to OpenGL 2D window. And so now the way we're going to draw is going to be rather different. So with the grids, with the GUI window grids, it's recommended that you loop over all of the pixels and set each pixel individually. With the OpenGL windows, they work instead with geometries. So the first thing you would do is clear the window and then draw in the shapes one by one. So we'll just write that out here. So the first thing we'll do is clear, and we can give it a background color, so give it black. And then we'll loop over all the agents, so I'm going to use this iter shortcut. And we're going to loop over everything in the grid. So for every cell in the grid, we will draw a circle. So we'll draw a circle, and we'll give it the x-coordinate, the y-coordinate, and the radius to draw. So we can just define a radius. These cells don't actually take up any space. They are existing as points. But we can, pretend that they do, at least for the sake of visualization, because we can't obviously visualize something with 0 radius. So we'll give them a radius of, 0.2, for example. And then we have to give it a color as well, which can be the cell's color. And then after we are done, adding all of our geometries, we have to show what we made. So it's the last thing. And now when we run this, it'll show the visualization, but in sort of off-lattice instead. You can see these little dot-looking cells moving around. So just for fun, we'll change the radius a bit, see what that looks like. The X button doesn't work here unless you sort of add it to the grid, and I'll show you that in a moment. Okay, let's set this to 0.5 and see what that looks like. Maybe it'll be a bit easier to follow. So you can see each of these cells is sort of represented as a circle, and the circle is obviously centered on the position of the cell. And the dimensions here are mapped to the X and Y dimensions of the grid. See, it's slowing down a bit even now. I mean, it is a lot of cells, but anyhow. So last I'll show you how to have the window disappear when you click the X button. And there's sort of two steps to this. One is you have to check if the close button was clicked, and we'll do that inside the for loop here. It's the it is closed button. And then we can just break out of the for loop at that point. So we want to exit this time step loop. And then the last thing we should do is close the window when we exit the for loop. That way the window will actually disappear. So now if I run this, we should be able to see the window properly close. So cool. I hope this was useful. Next time we'll do off-lattice agents that actually take up space and push apart from each other. So these agents, you could see them sort of freely floating past one another. That's not necessarily realistic for cells that form a tissue where they're rather constrained. So next time we'll look at how that is accomplished. All right, well, see you then.